Welcome back to the shop. Today's project is about modifying this off-the-shelf GoPro stabilization gimbal to work better for this robotics project where we're trying to make a little hovering camera that can follow my cat around. Something kind of like this cartoon drawing, a kind of flying camera that can hang out with my cat during these streams. I'll be modifying the gimbal to hold a different camera that can stream out uncompressed HD video over SDI. And I'll also be adding a LIDAR rangefinder in order to help the robot keep the camera in focus. Let's get started. Okay, so here's the one I've been using as the current Tuco cam. Yeah, I got mine on Amazon, but I guess wherever they were sourcing this from is out of stock now. But it outputs 1080p video over SDI, which you can run long distances over pretty cheap coax. It's a little tricky because of all the dangling wires at the moment, but I don't think I have a good way of getting the video out of the GoPro, because the SD analog video is not really worth bothering with. I don't want that. It has HDMI out, but that's even harder to deal with than SDI. Like, part of the reason I like that camera is that SDI, you just need one coax, whereas here, you need several twisted pair. And then yeah, Wi-Fi sometimes works, often doesn't. This gimbal is pretty nice. So the brand is Feiyu Tech, and it's the Mini3D. Let's see, this is the gimbal. And it was basically the sort of simplest, cheapest gimbal I could find that seemed like it would handle this camera and that was 3-axis, since I figured I would need 3-axis stabilization. It seems like a pretty nicely designed product. It also has some things that scare me. Make sure that the connection to the computer is done by the USB connector. So I'm really curious what this is. I have a guess, but I want to find out. Yeah, this is a USB serial adapter. It's a Scilab CP2102. Bunch of different firmwares, the update software, and some setting software, which could be interesting too. This actually turns the gimbal controller on and off. Heading, following mode, fast, normal, slow. It's pretty nice construction. Like, it's all like machined metal, and the two middle connectors are +12 and ground. Yeah, so that's mode switch. That's our pinout for this middle module that this is acting as a breakout for. It is mostly just built around all the motors, and it's really elegant. Like, it feels like there's another little wiring harness in there. Oh, it's a connector and a wiring harness. Oh, that is the cutest. It's also glued. Is that glue or lubricant? Seems like glue. Seems like silicone. I mean, if there isn't anything special going on, like a slip ring, and this is just going straight through, maybe I can have some coax join these wires, if I can find some coax that's thin enough. So you can probably see the neodymium magnets behind there. And then I can kind of feel this cogging a little bit as I rotate it. And so these 3 pins are going to be the 3 phases of this brushless motor. But yeah, one of those is going to be our lonely little video wire, just hanging out there with all these other signals and no shielding. And this does not look like a slip ring. This looks like the wires are just going through, and then you can see their end stops because it doesn't continuously rotate. So these are the output drivers for the 3 phases of the motor. Going straight to the motor. What was that we were looking at? The O12B1000? Yeah, so that's their magnetic angle sensor, Infineon. Or at least that's the closest match. Oh, it's so nice how all these parts are metal. STM32, we have a winner. Oh yeah, the other half of the H bridges are on the back side. So those 3 transistors and these 3 transistors are the motor driver. Magnetic sensor, op-amp, motor drivers over here, 3-terminal regulator, I assume, and a buck converter. It looks like these joints are mostly just held on with these 3 screws that go through down into the motor. This is the last joint. Got another one of those same sensors. That looks like the same board logo and everything. That would be pretty neat if all the joints were identical. Each joint is basically just a repetition of the same pattern. Inside these wider sections, there's a driver board. All the wiring is just passed through these just holes bored through the motors and everything else. So that's part of why this has the microcontrollers in each joint. So they use basically the same pinout for all the connectors. They have a really limited amount of space for wiring, so just like a little L bracket even. It's a very tiny piece. Oh, actually it's pretty close to right there. that joint between the lens and the body. Yeah, so I want to line up this axis basically with this plane between the two elements. Then there is the space for the L bracket that we've been talking about. Okay, is that it? So if we take off these other components, so take off the camera, take off the gimbal mount. It's looking printable. So this material is a t-glase. It's spelled T-G-L-A-S-E. And it's made from PET, so like water bottle plastic basically. So that's the motor housing. And underneath this cap is the accelerometer, gyro, whatever, IMU chip that they're using. So yeah, that's pretty nice. Feels pretty solid. This is a UFL connector, like you might have seen on Wi-Fi cards, covered with cat hair. The one on the right was what I got when I bought generic 0.81mm diameter coax on eBay. This is what the camera has in it right now. So that's the 42 gauge micro coax next to the 0.81mm. The other point of comparison, I guess, is the cabling that's already going through the gimbal. So the micro coax would be way smaller, and as you can see, the other coax is a little bit bigger. This gimbal is going to have a high-tech cat hair composite lubricant in it when I'm done with it. Hopefully it won't be too big of a problem. I'm like filleting the wire. Oh, that's a good sign. I think we are on our way to Gimbal Town. That video is going over this little tiny thing. This goes just like that. That was even faster. Oh, that's great. So, I'm liking that. So taking apart the first and last joints, I didn't actually take apart any of these pieces where we're passing signals through the little channel with the sticker over it. These are nice and long, because these go through the whole kind of circuit board compartment and then into the motor housing. So several of these have some silicone glue on it that I haven't taken out yet. The left connector top pin, that's where the video is coming in. That is going to be a no connect because we just cut that wire. This one's going to be no connect. This one is where we want the 12 volts to go. Since that'll be easy to get out. That's the actual 12 volt input, so literally I think we just want to bridge these two traces. Alright, that should be enough. And then a little bit of solder, a little bit of wire, and we should be good. No, that's probably just about right. Looking at how much clearance there is around the opening here because I don't want to squish the wire. Alright, that's the first joint plugged back in. Coax running through it. This is going to start getting hard to shift around, so I probably need to be careful to have this be the length that I want it to be before I put this joint together. Oh, the machining on this is actually really nice. Like these two pieces of the housing actually click together with quite a nice feel. It is at least nice to have a pretty good mix of countersunk and non-countersunk holes to give me some more clues about which fasteners go where. So we've got coax going through there. Ready to snap the motor in. 12 volts ground coax. Let's put this back on. So, as you can see, we've got the camera in the gimbal. Got this mapped up to an Xbox controller, same as last time. The way the software is written right now, this control stick and this stick are just mapping pretty much directly to like servo motor style RC aircraft kind of outputs. You turn it that far and then it would hit this back bracket. So then I just took this thing over to my belt sander, which is a little tiny belt sander, but you know, this is soft aluminum, so. And so this is actually not too bad as far as this axis is concerned. It's balanced pretty well and it's free to move. But the roll axis is really off center right now. The bracket that I designed is doing its best to keep the optical centers lined up. So like all it can do is be only as thick as the aluminum bracket. So by being only that thick, I'm doing my best to keep the optical centers lined. But then that has the side effect that I wasn't considering of making that axis really unbalanced. Oh, that's a good sign. I think we have a winner here. Okay. Oh, that's great. I mean, you can see some artifacts from the optical centers being lined up, but it's well within the tolerances of what I was expecting. Oh, and I've still got the power cable attached separately, so it's going to be even better once this isn't dragging, I think. So the LiDAR sensor, I think, might be a really good match for basically finding the focus range of the camera. The camera has manual focus. I would be setting it to a fixed distance that's just whatever I want for photography's sake. And then the robot would be adjusting its position to maintain, you know, roughly a fixed distance from the target I'm aiming at. For that, I think this might actually be a really good match if I can fit this on the gimbal so that it tracks with the camera. Before I even read the documentation, I'm going to take this apart. I think I can get into the back of this without opening the whole optics package. So the name of the company that makes this is Pulsed Light, and then the name of the sensor is the LIDAR-Lite. And their whole shtick is that it's supposed to be like a less expensive, lower power, more eye-safe, you know, intrinsically safe kind of LiDAR sensor because of the way it uses a bunch of fancy digital signal processing and a lower power but interestingly shaped pulse of light. I don't know what the CM is, but Lattice something or other Mach X02. So yeah, this is an FPGA. Great. And then a bunch of power supply looking doodads over here. And it looks like it's emitting from the side of the die. This is probably an infrared laser diode. I've just never seen a laser diode in a through-hole package like this before. So this is definitely separate stuff that's not the regular port or JTAG, but it is hacker-friendly. That's nice. Got some power supplies. Ooh, drawings. Oh, a block diagram. This is nice. So they tell us what's going on in their FPGA and in their analog. So that's great. That gives me the functionality I want. Doesn't have me relying on a potentially buggy expert C and lets me just use a single wire. So yay. And so one of the things I've done already is I went through the gimbal and, well, so first of all, I made some extra room in there by removing this wire that I didn't think I need that served the composite video from the GoPro back to what would normally be your first-person view setup. In hindsight, I could have used that wire for the LiDAR sensor, but you know, whatever. If I'm opening it up again, it's just as easy to add a new wire. So this is roughly balanced. It's a little bit heavy on that side now, which means that this piece actually needs to be a little thinner than my mock-up. I don't quite know by exactly how much, but I'm probably just going to guess, and it'll get the balance close enough. But yeah, this gimbal contraption is looking pretty interesting. It definitely looks a little more menacing now that it has like 3 eyes, and it's like, and like one of these is literally a 1-watt laser with low duty cycle drive, you hope. If you've seen these sensors before, they usually have these back covers with these little ears that stick out. I tested it, and the ears are actually definitely wider than I want this gap to be, so no ears here. LiDAR-Lite housing. Oh, this seems super useful, great. Let's import this into Fusion 360. I wanted to leave this connector available. That's the connector that initially went to this cable, the thing that originally went through the back housing of the camera. So this is power, composite video, and all the buttons. And the buttons, I haven't looked at how they're wired totally, but there are 4 I/O pins and a ground, and there are 5 buttons. So there's some kind of multiplexing going on, but I haven't checked whether it's like resistors or a matrix or what. So I'd like to keep this connector intact so I can just plug this in. But that also means that now I kind of lose the ability to use the +12 on this connector, which is usually how this camera gets power. Oh, this is nice. This is just like their actual CAD model for the plastics. This has all the features. That is beautiful. It's got their feedback path. So this is like the little thing that holds the filter. They've got the feedback path between here and the diode over here. This is the baffle between their laser diode and the monitor photodiode. Because this is pretty much exactly what I want, but without the mounting ears and with an attachment to the rest of the camera. Yeah, now we're getting a sense for how the mounting works in here. I'm going to fuss with this a little more just to make sure this is right, but I think this position might be correct relative to the other parts we have here. So that's going to be like the side of the mount that presses against the camera. There's the thing. That's closer. There's a good bit of structure around there. So like this is going to be where I'm putting a bunch of the anchoring force and then trying to distribute it back toward these posts, and I think that's going to work out all right. Okay, so starting at the bottom, we have the brim and the first layer, and we're making room for the screw. So the manufacturer helpfully had CAD files for the actual plastic pieces up on their website. And so you can see I've modified that and made it a lot thicker, added a place for a screw to go in that way, added another little bit of interfacing just to kind of fill in this gap, but some room for the wiring to go through and for the connector to still hang out in between there. That's what we've got. So this Kapton tape is replacing the 3 screws that I think Tuco is sitting on. Got this bracket. It screws onto the side of the camera. Yeah, I think that's fine. It's putting some tension on the wires, but I think the wires will handle it fine, and this will just clamp a little bit. So I made one tweak, and so actually the one you see on here right now is a slightly tweaked version relative to the one from last time. And it balances better, but I think I can still do a little better. The limitation we're about to run into is the distance between this little connector and the side of the camera body, which is already really tight. There really does not seem to be enough room for the wires there. So another option would be to redesign this so that the LiDAR mounts the other direction. So the connector comes out on this side, and then I have a little channel for the wires to route through that direct them that way. And then the other solution, which I think I'm leaning toward, is just to remove this connector and solder 3 wires where it would have gone, and then to use this much thinner bracket that I just printed. Oh, that one worked. Maybe I was just going about this from the wrong angle. Well, let's see what the damage is. Yeah, I mean, hot air would have been nicer. I just didn't want to damage anything else on the board, especially the laser, because I don't know how sensitive this stuff is. Ooh, that's looking good so far. So then, will this fit with the optics installed? Yeah, it fits. Well, the plastics fit at least, which it didn't before I removed that connector. That is still maybe a little bit that way heavy, but much closer to balanced, and I'm not printing another bracket unless I have to. This is looking quite good enough. So see this bracket, if I was reprinting it, I would definitely have a cutout there so I could get the wires in and out. It would be slightly less strong, but I think it's still strong enough even with that cutout, and it would be easier to put things together. This is the IMU, which I assume runs off of 3.3 volts, and this would be a 3.3 volt regulator. Yeah, there is not room above the connector. I have to move it to the side of the connector and avoid the pillars. I think there's room for 2 more wires without taking this connector off. So I think I'm going to kind of keep these together as a little bundle, and then this one will break out and go over to the left, so the wire length as it is actually probably fine. Yeah, that is a monster heatsink. Because it's not only the ground plane, but also the metal case, probably. But I think that's enough to start. So, Now we have all of this wiring on the back of the camera done. If we had a cover to put on this, this is when we put the cover on. So maybe this is time to model a cover. So these have already been scaled from whatever the joystick maximum is to plus and minus 1. And so I think want to cut this way down and set the X and Y to something like 400. And you can kind of see how this is working. And I haven't been paying much attention to it, but you can see the data from the LIDAR. That's looking about right. So longer pulses there mean farther away. Good signal from the LIDAR too. At that distance, it's definitely in the frame that the LIDAR is pointing at. What is that? Oh, is that a light leak coming in the back? Oh yeah, that might be another reason to have a wiring cover. Because I was thinking about light leaks earlier, but we hadn't really gotten around to addressing that. And I think that is coming in the back of the camera. Is that looking a little better? I think my Rube Goldberg machine of video splitters and things are causing somebody to disagree about frame rates in a way which OBS is not happy about. Now we've got, this is as close to the raw feed as I'm probably going to have for the future. When it just drops up and down like that, that is me crossing really quickly over what it thinks is the dead zone on the y-axis of the joystick. So like it may look a little unintuitive, but based on how it feels with the joystick, it seems like that's what it's doing. So I think once I figure out how to either cook my inputs a little better in my code or update the firmware on the gimbal, then we should get past that problem and we'll be able to move this more smoothly. Okay, so I'm holding the gimbal now and just moving it around. And so you can see it shifting around a little bit, but like given how fast this is going to be moving as the cat cam moves, I think the stability is going to be totally fine. I don't know, maybe that gives you a better idea of what this is doing. That top right picture-in-picture is coming from the camera on the gimbal. Yeah, so this is our tasty little gimbal. And it's actually fairly balanced, a little bit heavier on the LiDAR side, but so if we wanted to, we could add some weight on that side with the plastic bracket, but also kind of just don't necessarily want to add weight because it's already pretty well balanced. So I think I want the wire cover to just anchor on this side and then just basically kind of swoop over here and follow the curve of the back of the camera, keep the wires down so that they don't hit this gimbal, and provide a guide for the wire to come in on this edge. So that basically I can leave enough wire slack in here so that I can take it apart. Otherwise it just wouldn't be possible. But I still have a way of kind of pushing that together when I need to assemble it. That is much better. So we've got this nice little bar to stabilize this horizontally. Then it'll come up and make kind of a nice uniform cover, and there'll be plenty of room for wiring in all of this area that's full of support right now. This mess on my desk here. So some of you might not be familiar with this stuff that exists. So black hot glue. I first heard about this from Applied Science, Ben Krasnow. That's a thin little puddle of this stuff and pretty bright flashlight. Here's a bigger piece. And you just don't see any light through that. It's very heavily loaded. And you can take it off with isopropyl alcohol just like you can with regular hot glue. Although, as you can see, sometimes you can make a mess by leaving some of the pigments and a little bit of glue residue behind. I think I just need a cutout for the coax. Oh, that's super long. Because if that's what I need, then this will need to be more supported. Yeah, okay, so the right side looks great. This is flush against the circuit board. Gives me a nice kind of intentional opening for that connector. Hides all this junk, gives me some stabilization. Then we've got some problems. So the heatsink, definitely closer to the edge than I thought it was, which would mean that this already thin piece needs to be even thinner. I like the exposed heatsink a little bit too. It's like, looks like it is as power hungry as it is. Just make this 6 instead of 6.8, and that might be what we want. But then I definitely want to reinforce all this other stuff, because that's going to be really weak otherwise. And then depth, I'm going by basically how far down on the cable do I have to go before... Hey Tuco, you found my space mouse. Yeah, that's more like what I wanted. Still plenty of support around there, but a lot of room for this cable. So then we've got the pillars that it ends up sitting on the circuit board with. Then we already start supporting that really thin region over there. That's looking pretty printable to me. There are some places where it wouldn't be bad if I got hot glue on the wires, but I'm mostly trying to avoid getting hot glue on the wires and just using it to block the light around the edges of the circuit board. This is going to be pretty effective at light blocking though, because it's just so opaque. And so dribbly. I think that's going to be alright, and the hot glue actually kind of provides a little bit of nice cushioning in some of the areas. It doesn't seem to be deflecting it. I think that's going to be good once the printer finishes. Oh yeah. I think that's pretty much what we're talking about. We just need some screws. I think we might unintentionally have the hot glue acting as another layer of washer, but that's, whatever works. As long as it looks good and is reliable, it doesn't necessarily need to match the CAD model 100% in this particular project. Okay. The jerkiness you're seeing right now is mostly due to the controls. Like that little bit of wobble and overshoot as I was stopping, that probably was the gimbal's control loop. But the abrupt starting and stopping is entirely just the joystick here having an inconveniently sized dead zone for this application. That's me moving, I think, as fast as it'll let me go, side to side. And up and down it goes actually quite rapidly, it's easy to lose control of it up and down. So some tuning in the firmware for sure. Yeah. You can kind of get an idea of what flying over there might look like. So that wraps up the first stage of this modification project, giving our gimbal an SDI HD camera and a LIDAR distance sensor. Be sure to subscribe so that you don't miss the next episode where we dig into this gimbal's firmware, decrypt it, and patch it so that we can control the gimbal just how we want over the serial port. Also, if you subscribe, you can sign up for notifications for my interactive live streams where I record footage for these broadcasts. And a very special thanks to everyone who supports me on Patreon. You're keeping me motivated and, most importantly, keeping the lights on in the shop, helping me pay the rent. So I really appreciate that. If you're new here, check out my existing videos, and if you like what you see, maybe consider donating just $1 a month to help me keep going. My cat and I would both appreciate it a lot. And as always, happy hacking, and I'll see you on the next episode.